Hi everyone, welcome to Go Classes. In the last lecture we were studying how to convert English statement into first order logic. Okay, many examples we have seen, all the basic templates we have seen. Now in this lecture, in this video, we will see how to do numerical quantification. What is the meaning of numerical quantification? So numerical quantification means this type of statements like there are at least two objects, there are at most two objects, there is exactly one object, at least three objects, at most two, exactly two. This type of statements, how can we convert into first order logic? Okay, so let's see one by one. So let me give you a little bit review, a little bit overview of what we have seen. So this type of statement we have seen how to convert into first order logic. For example, every cube is large. Every cube is large means for all x we are saying that if it is a cube then it is large. If it is a cube then it is large. This statement, this type of statement we have already seen how to convert into first order logic. Okay, so this is one example. Let's see another example. No cube is large. What it means? It means there does not exist any x, there does not exist any x which is a cube and which is large. What it means? It means there is no large cube. This is the point. No cube is large means there does not exist any cube which is large. Okay, we can also say that for all x we are saying that if it is cube then it is not large. Negation of large. Okay, so very simple. Both are equivalent. Both these expressions are equivalent. This expression is saying that for all x in the domain, for all x we are saying that if it is a cube then it is not large. It means no cube is large. Okay, both are equivalent. Let's see the next example. Nothing is large. Now in this question he is saying nothing is large. Nothing is large means there does not exist any x which is large. So this is the point. Very simple. There does not exist any x which is large. Or we can say that for all x we can say that they are not large. Okay, negation of large. See the difference between here and the last sentence. This sentence is saying that nothing is large. Okay, and this sentence is saying that no cube is large. So in this sentence we have that for all cube we are saying that it is not large. For all x, if it is a cube then it is not large. But in this statement we are saying nothing is large means in the domain, let's assume this is your domain. So in the domain basically we are saying that nothing is large. It means there does not exist any object which is large. Okay, it means there does not exist. Okay, remember what this means? This means there exist. So this means there exists. Okay, and this means what this means? This means negation of there exist means there does not exist. Okay, there does not exist. Correct. Now so both are equivalent. You can see this is saying that for all elements in the domain we are saying that it is not large. Okay, let's see the next example. Some cube is large. It means there exists x which is cube and which is large. Correct, which is cube and which is large. So very simple. This is a standard template that we have already seen. You can watch the previous lectures and the link of the previous lectures you can find in the description or on our YouTube channel you can find. Okay, let's see next. All large cubes are nice. What it means? It means for all x we are saying that if it is large and it is cube. So basically we are saying that if it is large and if it is cube, okay, then it is nice. Okay, so this is very simple point, because this is saying all large cubes are nice. It means for all x we are saying that if it is large and it is cube means it is a large cube. Okay, if it is a large cube then it is nice. Okay, so this is how you can convert this English statement into first order logic. Next, there is at least one cube. Now this type of statement we need to see. Now this is saying that there is at least one cube. Okay, so this is very simple. We can say that there exists a cube. Okay, there exists x which is cube. So very simple. So this type of statement means at least one. So this is basically example of at least one statement. At least one. Okay, so you can see there is at least one cube. So how can I write? Very simple. There exists x which is a cube. So it means there exists at least one cube. Correct? Let's see next. There are at least two cubes. Okay, there are at least two cubes. Means there must be at least two different cubes must be there. Now how can we convert this into mathematical logic? How can we convert this English statement into first order logic? There are at least two cubes. Okay, so the first thing that will come to your mind is like this. There exists x, there exists y, such that x is also cube and y is also cube. This is the first thing that will come to our mind. Correct? But is it correct? Okay, see, this is the first thing that will come to our mind when we see this. There are at least two cubes. It means there exists x, there exists y, such that x is also cube and y is also cube. But this is not a correct expression. Why this is not a correct expression? Let me tell you. See, this is not a correct expression because consider the situation when there is only one cube. Let's assume in the domain there is only one cube. Let's assume this C1. This is the only cube. Now you can notice that there is only one cube. So this statement should be false. Okay, this English statement, there are at least two cubes. This English statement should be false because in our domain we only have one cube. So this English statement, there are at least two cubes, this English statement should be false in this scenario. Correct? But you can notice that this first order logic expression, this expression will be true. Very easily you can see, because what you can do, see, the domain of x is also this and the domain of y is also this. So x, this variable x is also pointing in this domain and variable y is also pointing in this domain. Now you can notice that when x is also pointing to C1 and y is also pointing to C1. See, this variable, when this variable is also pointing to C1 and when this variable is also pointing to C1. Okay, in that scenario you can notice that this first order logic expression, this will become true. Okay, you can see, because there exists x, there exists y, such that x is also cube, y is also cube. Now very easily you can see that, okay, there exists x, so you can take C1, so you can take x equal to C1. There exists y, you can take y equal to C1. Now you can notice that C1 is also, this x is also cube, y is also cube, because both are C1, x comma y, both are pointing to C1. So this first order logic expression will become true. So you can notice that when there is only one cube, there is only one cube here. We don't have two cubes. There is only one cube. In this scenario, you can notice that this English statement will become false, but our mathematical expression, this first order logic expression, will become true. So we can say that this is not a correct expression for this statement. For this English statement, this expression is not a correct mathematical expression. So what is the problem here? You can notice what is the problem. The problem is very simple, because just because we are writing x and y, that does not mean that they are different, because the domain of x is also this and the domain of y is also this. So this variable x can point to C1 and variable y can also point to C1. So that is the problem here. So what we should do? Okay, can you think about it? Yes, very simple. Just take x not equal to y, because we want at least two cubes. We want at least two cubes. So what we can do here? So here just a small modification we need to do. What we need to do is just that there exists x, there exists y, such that x is a cube and y is a cube and x is not equal to y. This is the only modification we need to do. Now you can notice, now very easily you can see that there exists x, there exists y, okay, such that they are different, means there are two different objects. First of all, x and y are different, means there must be two different objects, such that x is also cube, y is also cube, means x and y should point to two different, because x and y are different. So x and y should point to two different objects, such that x is also pointing to cube and y is also pointing to cube. So that is the reason we can say there are at least two cubes. correct? So this is the expression for there are at least 2 cubes. Okay, so if there is any doubt you can ask in the comments. So let me just write once again. There are at least 2 cubes means there exists x, there exists y such that x is also cube and y is also cube and x should not be equal to y. Both must be different. Both cube must be different. So this is the formula. This is the first order logic expression for this statement. Okay. Now let's see in general. If you want to say that there are at least 2 items in the domain, if you simply want to say that there are 2 things, okay, this statement, there are 2 elements. There are 2 elements in domain. In the domain. So how can you write it? This English statement, there are at least 2 elements in the domain. So how can we write? Very simple. There are at least 2 elements in the domain. So we can write it very simply. There exists x, there exists y such that x is not equal to y. Very simple. You can notice when this will be true. This expression, this mathematical expression will be true when there are at least 2 elements in the domain. So when in the domain, when you have at least 2 elements, then we can say that this mathematical expression will be true, and this is what we want. There are at least 2 elements in the domain, so you can write very simply like this. So for this statement, for this English statement, the correct mathematical expression is this. Okay. Let's see the next, that is there are at least 3 cubes. Now this is also very simple. Okay, what we can say there exists x, there exists y, there exists z such that x is also cube, okay, and y is also cube and z is also cube, because there are at least 3 cubes. So it means there exists x, there exists y, there exists z such that x is also cube, y is also cube and z is also cube, and they must be different. So and I can say that x is not equal to y and y is not equal to z and x is not equal to z. All these must be different. So this is the expression for there are at least 3 cubes. Okay, so very simple. You can notice there exist x, y, z. There exist 3 objects such that x is also cube, y is also cube, z is also cube. And you can notice they must be different because we want at least 3 cubes. So x should not be equal to y, y should not be equal to z, and x should not be equal to z. So this is the first order logic expression for this English statement. Let's see. If we simply write, if we simply want to say that there are at least 3 things in the domain. So in the domain there are at least 3 things. If we want to say this, then how can we say? Very simple. There exists x, there exists y, there exists z such that x is not equal to y, y is not equal to z and x is not equal to z. Very simple. Means we want at least 3 things. It means all the 3 things must be different. Okay. So this is how we can write this English statement into mathematical expression. Let's see next. There is at most 1 cube. How can we write this? There is at most 1 cube. So very simple. What it want to say? It want to say that there is at most 1 cube. Okay. So there are 2 ways to write this. Let me tell you both the ways. So first way is at most 1 means there is no cube or exactly 1 cube. Correct? Exactly 1 cube. Correct? Because there is at most 1 cube. At most 1 cube means there is no cube or there is exactly 1 cube. Now we have not seen how to write this exactly 1 cube. We will see. Okay, just after a few minutes we will see how to write this exactly 1 cube, how to write this. But we can write this, there is no cube, means there does not exist any cube. There does not exist any x which is a cube, or there is exactly 1 cube. Now we need to study how to write this statement, exactly 1 cube. How can we write this into mathematical expression? That we will study now. But this is one way. Okay, once we study this we can replace here. Okay, now let's see the other method. What is the other method? There is at most 1 cube. What it means? it means that finally why I can say that it means that for all x, for all y, I can say that if they are cube, then they are same. Okay, this is the very simple method. There is at most one cube. It means I can say that if there are two cubes, okay, then they are definitely same. So this is what I want to say. I want to say that for all x, for all y, I want to say that if they are cube, okay, if x is a cube and if y is a cube, if x is a cube and y is a cube, then they must be same. So this is how I can write. Okay, so very simple this. Okay, see what we are saying. We are saying that there are at most one cube. What it means? It means that if there are two cubes, okay, if there are two cubes, cube x and cube y, then they must be same, because we cannot have more than one cube. So we cannot have two cubes. We cannot have this two cube. It means if both are cube, they must be same. Okay, now you can notice very easily that in this expression you can notice that we cannot have more than one cube, because if we have more than one cube, then what will happen? Then this expression will become false. Okay, so this mathematical expression will become false when we have more than one cube. Okay, very simple. Now you can notice that this mathematical expression is telling us that for all x, for all y, we are saying for every two elements, whatever two elements you take, for every two elements we are saying that if they are cube, if x is cube and y is cube, then definitely they are same. You can notice one thing, that if there is only one cube, now you can notice this statement will become true. Okay, if there is only one cube. And you can also notice that if there is no cube, let's assume there is no cube in the domain, we don't have any cube, then also this expression will become true. Why? Because when there is no cube, then you can notice this expression, okay, this expression will become false for all x, y. Whatever x, whatever y you take, now you can notice that if there is no cube, then this expression, this antecedent of implication will become false. And you know, when this antecedent of implication becomes false, then the complete expression will become true. So what I am saying that this expression, this mathematical expression will become true when there is no cube or when there is one cube. Okay, and when there is more than one cube, then this mathematical expression will become false, and this is what we want. We want at most one cube. So we want our mathematical expression to be true when there is no cube or when there is one cube. In this scenario, we want our mathematical expression to be true, and this is what is happening. Okay, so very simple. Now let's see another point. What is that? Basically, whenever you want to say that there are at most one thing, okay, whenever this statement you want to say, there is at most one thing in the domain. Okay, so this statement, there is at most one element in the domain. So how can we write this statement? There is at most one element in the domain. So how can we write? Very simple. We can say that for all x, for all y, what we can say? We can say that they are basically same. We read this statement. This is saying there is at most one element in the domain. So we can say for all x, for all y in the domain, whatever two elements you take in the domain, they are same. What it means? It means that there are at most one element, because this expression is saying that whenever two elements you take, whatever x comma y you take, they must be same. Okay, now you can notice this mathematical expression, this is true when there is no element. When the domain is empty, we know that when the domain is empty, then this quantifier, universal quantifier, will become true. And when there is only one element, let's assume there is only one element. Okay, when there is only one element, in that scenario also this expression will become true. And when there are two elements, let's assume more than one element when you have, in that scenario this expression, this mathematical expression, will become false. This is what we want, because we want there is at most one element. It means we can say that for all x, for all y, we are saying that x is equal to y. Okay, so very simple scenario. Let's take one more example. If I want to say that there is at most one, I can say there is at most one bird. So how can I say? Very simple. There is at most one bird. So I can write like this. We are basically saying that for all x, for all y, we are saying for every two elements we are saying that if they are bird, if x is bird and if y is bird, then definitely they must be same. Correct? If they are bird, then they must be same. So very simple, because there is at most one bird. What it means? It means for all x, for all y in the domain, we are saying that if they are bird, then they must be same. Okay, if they are bird. If they are not bird, then that is fine, because if they are not bird, then this will fall, this will become false, and because this will become false, so this internal expression, this expression will become true. But you can notice, if they are bird, if x is bird and y is bird, then definitely they must be same, because we want that there is at most one bird. There should not be more than one bird. So if there are two birds, then they must be same. So this is the point. Okay, for all x, for all y, if x is bird and y is bird, then they must be same. This is the meaning of there is at most one bird. Okay, let's see the next. There is exactly one cube. Now this expression, there is exactly one means it means there should be one and there should be exactly one, not more than one, not less than one. So how can we write this? Okay, so let's see how can we write this. There is exactly one cube. Now this, there is exactly one cube, I can write like this. First of all, there must be at least one cube. Correct? There must be at least one cube, and there must be at most one cube. Exactly one means, see, at exactly one, it means there should be at least one cube and there should be at most one cube. Okay, when there is at least one and at most one, it means there is exactly one. Now what is this? At least one cube means there exists x, which is a cube. Okay, this is there exist, this means there is at least one cube and there is at most one cube. How can I write? Just now we have written this. At most one cube means for all x, for all y, if they are cube, if x is cube and if y is cube, if x and y are cube, then x must be equal to y. Okay, so this we have already seen. So this is one way. You can notice there is exactly one. Exactly one means not more than one, not less than one. So I can say that there must be at least one, there must be at least one, and there must be at most one. So there is and here. So when it will be true? It will be true when there is at least one, and it will be true when there is at most one. So what is the meaning? At least one and at most one means there is exactly one. So this is one way to write it. Okay, there exists x, which is a cube, and for all x, for all y, if they are cube, then x should be equal to y. This is one way. Let's see another way. Okay, let's see another way. What is that? The another way is this. First of all, exactly one means there should be at least one, right? So I can say there exists x, which is a cube. First of all, I can say there exists x, which is a cube. Okay, and so it means, remember, it means that there is at least one cube. So far it means there is at least one cube. So far at least one, because there exists x, which is a cube, and now not more than one. It should not be more than one. Okay, because exactly one means not more than one. So I can say, and for all y I can say, that if it is a cube, if y is a cube, then it must be same as x. Correct? So very simple. Okay, you can notice what we are saying. We are saying that there is exactly, this is what we want. There is exactly one cube. So what I can say? I can say there is at least one cube, there exists x, which is a cube, and now after this if something is cube, then it must be x. Okay, because more than one cube should not be there. So what I can say there exists x which is a cube, and for all y I can say that if y is a cube, then definitely x must be equal to y. Okay, so this is how I can write there is exactly one cube. This same expression I can write like this. This same expression we can also write like this. What we can do? We can do this. There exists x for all y. What we can say? There exists x for all y. This x must be a cube, and if y is a cube, then y must be same as x. So this is another way to write it. Both are same, both are correct. Okay, no problem. Both are equivalent actually. Both are saying the same thing. Okay, so this is another way to write this expression. Now let us see, is there any other way? So we have already seen two different ways of writing this statement into first order logic. Now is there any other way? Yes, there is. Okay, so you can notice this is saying that there is exactly one cube. What it means? See, it means that there is a cube, means there exists a cube. So there exists x which is a cube. So this x is a cube. Definitely this x is a cube. Okay, this x is a cube. And if something is cube means if y is cube, then this y should be equal to x. So this is the simple way. This is the simple thought process. I am just telling you what is the thought process. There is exactly one cube. It means there exists x. There is some x which is cube. Definitely. Okay. Exactly one cube means there is at least one cube. Means this x must be a cube. And also, if something is cube, if y is cube, then definitely y must be equal to x. Now we can combine these two, and what we can write? We can say that there exists x for all y. This is for our cube. There exists a cube. Okay, and what this means? This means for all y, basically if y is cube, then it must be equal to x. So what I can say? I can say that if y is cube, then it must be equal to x. Okay, and this x must be a cube. Okay, x must be a cube. If y is x, basically, then it must be a cube. Okay, so this is how we can write. Okay, just understand this. This is a little bit tricky. Now you can notice we are saying that there exists x for all y, means there exists a cube. This x must be a cube, and for all y we are saying that if y is cube, then y is equal to x. So you can notice that if y is cube, then definitely y is equal to x. So this arrow. Okay, now this arrow we have. So let's see this arrow that we have, because if y is cube, then y should be equal to x. Okay, and also this x must be a cube, means when means when this y is equal to x, then it must be a cube. Okay, so this is the point. There exists x for all y. It is cube if and only if x is equal to y. Okay, so this is the point. You can notice that this statement will be true when there is exactly one cube. When there is exactly one cube, so what we can do? So it means when there is exactly one cube, it means what will happen? It will happen that this let's assume there is exactly one cube, C1. Now in this scenario, what will happen? So this x is C1, and you can notice that for all y, you can notice that when y is C1, then this is true, and because C1 is cube, so this is also true. So you can notice that this statement will become true. This expression will become true when there is exactly one cube. Okay, so I hope this is clear. So let's take one more example. There is exactly one bird. See, now I am writing it again, and if in the previous example, if you could not understand, then focus here. What I am saying there is exactly one bird. Exactly one bird means there exists a bird. Definitely there exists x such that this x is a bird. This x must be a bird. Okay, And for all y, we can say, for all y, what we can say, if y is a bird, then y should be equal to x. Okay, so this is what we want to write. This is the idea. Means there exists a bird, and for all y, if y is a bird, then y should be equal to x. So what I can say? I can say that there exists a bird, means there exists x. This is for bird. There exists x. For all y, we are saying that. For all y, we are saying that. So we are saying that, basically we are saying that y is a bird if and only if x is equal to y. Okay, so this is the point. Y is bird if and only if it is x. So it means, see, this is if and only if. If and only if, it means that when y is x, then it must be a bird. Okay, so there exists x, it must be a bird, and whenever y is a bird, for all y, whenever y is a bird, then it must be equal to x. So this is the point. If and only if means there exists x for all y is a bird if and only if x is equal to y. Okay, so this is the point. So these are the three different ways that we have seen. Okay, we have seen this way. Here we have at least one, at most one, at least one and at most one. Okay, and this is another way. There exists a cube, and for all y, if y is a cube, then y is equal to x. This is little bit more tricky, so you have to work it out. Okay, just work it out. This is easy. We are saying that there exists x, which is a cube, and for all y, y is a cube if and only if x is equal to y. See, this, because of this if and only if, see, because of this is if and only if. Because of this, we are saying that x, if x is equal to y, then definitely it is a cube. So it means there is at least one cube. Okay, there is at least one cube. And if anything is cube, for all y, if y is a cube, then it must be equal to x. Okay, so these are three different ways of writing the same expression. Okay, now let's see this variation. There are at most two cubes. Do you remember we have already done at most one cube? Okay, this we have already done. There is at most one cube. So for this, what we did, do you remember? So we did like this. There is at most one cube. It means for all x, for all y, we said that if x is cube and y is cube, then x must be equal to y. This is what we did. Right? There is at most one cube. It means for all x, for all y, we are saying that if they are cube, then they must be same, because there is at most one cube. Now you can notice there are at most two cubes. So how can we write this? Very simple again. At most two means more than two must not be there. More than two must not be there. So we can say that for all x, for all y, for all z, we can say that if x is cube and y is cube and z is cube, if all are cube, then what should happen? If all are cube, then what should happen? Then definitely two of them must be same. Then either x should be equal to y, or y should be equal to z, or x should be equal to z. So this is how you can write. Okay, very simple expression. Okay, the same idea we are using here. You can notice there are at most one cube. So we are saying that more than one should not be there. It means for all x, for all y, if x and y are cube, then definitely they must be same. Okay, definitely they must be same, because more than one should not be there. Now here we are saying there are at most two cubes, means more than two must not be there. So if there are three, for all x, for all y, for all z, if they are cube, okay, if x is cube and y is cube and z is cube, if all are cube, x, y, z, if all are cube, then what should happen? Then definitely two of them, at least two of them must be same. So x equal to y, or y equal to z, or x equal to z. So this is the meaning. Means there must be at most two cubes. Next example. So let's see. So this is the idea. Let's see the next. There are exactly two cubes. So how can you write? Exactly two cubes means not more than two, not less than two. So first of all, exactly two means there must be at least two cubes. There exists x, there exists y, Remember, exactly 2 cube means, first of all, there must be at least 2 cubes. So there exists x, there exists y, such that x is not equal to y. They must be different, and x must be a cube, and y must be a cube, and we are saying that whatever else is cube, that must be either x or y. So basically I can say, and for all y, if y is a cube, if y is a cube, then definitely either x must be equal to this, y must be same as x, or this y must be same as, for all z, because this y we have already taken. So let's take all z, means for all z, we can say for all z, see what we can say. We can say that for all z, if z is cube, then definitely this z must be either same as x, or this z must be same as y. So this is the point, this is the expression. So the idea is very simple. The same idea we have applied in our, there is exactly 1 cube. Do you remember this? Exactly 1 cube. So how did we do it? Exactly 1 cube means there must be at least 1 cube. First of all, there must be at least 1 cube, and whatever else is cube. For all y, if y is cube, then this y must be same as x. This is the idea. This same idea we are using here. Okay, there is exactly 1 cube means, first of all, there must be at least 2 cubes. There exists x, there exists y. X and y are different, and x is cube, y is cube. And for all z, if z is cube, then definitely z is either equal to x or z is equal to y. So this is the idea. Okay, so this is the point. There is exactly 2 cubes. So we have seen in this lecture all the numerical quantification. We have seen how to convert at least 1, at least 2, at most 1, at most 2, exactly 1, exactly 2. So this type of statements, how can we convert into English language, from English language to first order logic, that we have seen. Okay, we will do some more practice in the next video. Okay, you can watch the previous lectures, and the link is in the description, or you can go to our YouTube channel and you can watch all the lectures. Okay, and if there is any doubt, you can ask in the comments. Okay, thank you everyone. See you in the next lecture.